All right, welcome to the very first calculus video. So this is what my voice sounds like when you can't see my face. Basically I'm going to just sort of show you an element of math that I believe to be pretty foundational. That's what these videos are usually going to be, some foundational knowledge that's important to your learnings, and then in class we sort of get to extend a lot more. And usually we follow up these videos with some sort of survey, couple questions, 1, 2, 3, 4, just depends on sort of what the topic is. So today I want to talk to you about CERs in math, claim evidence reasoning. So probably if you've been going to this school for a little while, you've done these in your math class. And you definitely have done them in hopefully your science classes as well. But if you're new to this school, or maybe you just have forgotten, here's just sort of a reminder. So today we're going to do a claim evidence reasoning problem on this. So the question is, does the function y equal f of x have a discontinuity? If so, what kind? Removable, jump, or infinite? Cool. So let's talk about sort of some pre-calculus knowledge and stuff we have that can help us out here. So let's sort of think about what we'd want to do. So the first thing sometimes you go for is, because it's in the order, right, is claim. Like, what is my claim? The thing is you don't know what your claim is yet because you haven't done any sort of work to try to figure this out. You could take a guess, but you might be wrong. So we don't start with the claim usually in math. We start with the evidence. So we sort of work out some stuff, do some math, try to show something, and ultimately convince yourself as to what your claim should be. So we're going to start with the evidence here. So let's think about the difference between removable, jump, or infinite. So a removable discontinuity is another name for like a hole. So I'd want to try to figure out, like, if it's removable, is it like one of these scenarios where there's like a hole in the graph, or maybe like there's, you know, the actual defined point is elsewhere? That's removable. Or is it a jump, in which case it is something like this, and then it jumps to a different place? The point can be defined elsewhere. It doesn't have to be one of these endpoints. So it would not be removable in that case. It would still be a jump discontinuity. Or last thing, maybe it is an infinite discontinuity, in which case it approaches one of the infinities as it approaches some input value, in this particular case as x equals 0. And sometimes even in those cases you can actually define the point elsewhere and it's still infinite discontinuity. So I need to figure out, like, which one of these is this one here? So this has to do with what our first topic is going to be about, which is limits. We want to basically figure out, like, well, what's happening as we get close to some input value of interest. If we look at the domain up here, it appears 0 is sort of our point of interest here. So as we get close to 0, like, is the left and right side approaching the same place, but then it's just like an empty hole? Are they approaching different things? Or perhaps are they approaching infinity? So to figure that out, I'm gonna do the limits here. So let's talk about limits here. You should have seen them at some points, but I'm just gonna do it real quick. So we're gonna talk about the limit as x approaches 0 from the left side for f of x. So looking from the left side, as we're coming in from the left side, well, if we're looking at the left side, we're interested in this formula here, because it says as you're approaching 0 when you're less than 0. So in other words, I want to know, what is the limit as x approaches 0 from the left of 1 plus x squared? So what happens as you get close to 0 to this parabola from the left side? Like, you can graph it to sort of see what's going on, but I think intuitively we can see, like, well, if I just plug in 0, I know that I'm approaching the output value of 1. It's actually the vertex of that quadratic function. So, all right. Well, hey, that actually matches up with what the actual value at x equals 1 the function is giving us. So when x equals 0, y equals 1, and this is approaching that. So it would appear that what we have going on is that the left side is approaching the actual point. So like sort of the opposite of this. As we approach the left, it would be actually defined here. So I'm guessing right now we're not thinking removable. The only worry I would have is what if the right side here were going upwards towards infinity? Okay, so I'm going to go ahead and find the limits from the right side. The limit from the right side. As x approaches 0 from the right of f of x. Well, since we're looking from the right side, okay, I want to look at this formula here because that's saying when x is bigger than 0, so that would be on the right side of 0. So I want to think about that. Once again, this is a quadratic equation, so we could theoretically graph it and sort of see what's going on too, but again, intuition should tell us like, hey, I could just plug in 0 and get it. So when I plug in 0, I get 4. All right, so it is not heading towards infinity, neither one of these, so it's definitely not an infinite discontinuity. And since the left side is approaching the actual defined point, it's not a removable. The defined point would be elsewhere, and plus the left and right side would both be approaching the same thing. No, what we got here is a jump discontinuity because the left-hand limit and the right-hand limit are not approaching the same value. So that helps me fill in my claim now. So what is my claim? My claim, does the function have a discontinuity? F has a jump discontinuity at x equals 0. That's my claim. And now, to finish it all off. So the last part of a CER is the R, which is your reasoning. And here, we want to restate the claim and explain how we know that based off of the evidence there. So why does the evidence prove the claim? So here we go. F has a jump discontinuity. Oh boy. I can't spell today. Discontinuity. Oh Lord. At x equals 0 because the limit as x approaches 0 from the left of f of x does not equal the limit as x approaches 0 from the right of f of x. That wouldn't be enough. So if they were equal, then we would have possibly a removable. But since I'm saying they're not equal, it would have to be one of these two. So the infinite discontinuity, I drew it this way, but it could be that the other one goes the other way. So what I want to add is f is a jump discontinuity, has a discontinuity at x equals 0 because the limits, left and right hand limits, do not equal the same thing. And neither limit goes to infinity. So if one of them went to infinity, then it would actually be an infinite discontinuity. So now I've sort of covered all my bases. They both approach defined values, 1 and 4. So, and since they're not the same value, we know there's some sort of discontinuity. And since none of them are infinity, we know that it is going to be a jump. So there you have it. That is a CER in math. So to recap, we start with the evidence to sort of figure out what our claim would be, fill in your claim, and then fill in your reasoning. I know it feels weird to sort of go like, well, I just wrote my claim, why do I have to state it again? But you have to remember how a reader would be reading this. The reader would start with the claim, look at your work, and then finish up here and go like, okay, like that all makes sense. So we use these quite a bit. You'll see them in the coming weeks a lot. And so I wanted to make sure that everybody was on the same page as to what constitutes a CER in math. So I hope this helps. And please take the little survey so that way I can get your feedback on stuff and see where you're at. Thank you so much.